Chaitanya and Sri Vignesh, am I audible? You are able to see the screen?
Yes, ma'am. Good morning.
Good morning. Is my voice low? Because I cannot get acknowledgement.
No, ma'am. It's perfect.
Okay, fine. Okay. So today we are going to see ABL trees. So I will give you a background of what ABL tree is, and I will also tell you the operations we will do. Before I go into ABL trees, I want to do a quick reminder that the assignment one is posted in the eLearn portal. So please complete the assignment one. Okay. Uh, any questions you have related to the assignment?
Since morning I was checking that only, ma'am. Assignment.
Okay.
What is it? Yeah.
Okay.
Yeah, it is bit complex and long also. Need to go through the document total.
You have to look at it step by step.
Yes.
Okay. It is a real-time application, but it is not the same algorithms which we have used in the class only. It is going to be there. Okay.
Yes.
But it is a cumulative application where it uses many functions which we have used in the class together.
Hmm.
This understanding is highly essential. So that is why I have given this as an assignment. If you have all these bits and pieces of the algorithm together, but you have to combine all this such that it works in a flow. That is the idea behind the assignment also. Okay. So read
Yes,
it
ma'am.
carefully. If you have any doubts, you can reach out to me uh, in terms of how to implement, or if you have some doubts, you can reach out to me, or you can also ask the lab instructor. You can email him and ask your question. Okay.
Sure, ma'am.
I will also, since you feel it is complex, what I will do before starting the class, let me just give a small overview of the assignment.
Yes.
Okay. So the assignment is to do a task management system. Task management is you in Jira, you would have used, if you're working in products, you would have used some softwares like Jira, etc.
Yeah,
Right?
ma'am.
So
Yeah.
a simple version of that is what we are actually doing here. Okay, that is a very complex. Jira is a very complex software. We're not going to go with that kind of a software. Here we are going to go with a simple software. The main job is you can add task, you can add subtask, you can mark tasks as completed, you can undo last action, you can you can complete a task, you can redo the last action. So simple things only we are going to, and we are going to do display. So when you create a task, just instead of creating numbers like 1, 2, 3, we are creating a task with a specific format. Okay, every task created should have a unique ID. First four digits represent the year, the next four digits represent the project, and then we have a 3-digit serial number. So this is how you create a task. So if, for example, IDs are given. So this is will be a task ID. Okay. Now you have to select a data structure. Now this data structure will have it is one data structure will not be sufficient, because we have undo redo, which is like a stack. Okay, whenever we want to do undo redo, like last in first out option has to be there. So we need stack for that. And since we have to maintain what is a task, what are the subtasks in it, what is completed, you also need a list approach. Okay, so we might need two data structure. So these are the requirements, and we have also given you the functions to be implemented. This you can modify slightly, but these are if you go by these functions, it will be easier for you. So first initialize a task list. Okay. Uh, uh, Initialize a list to maintain the task, then initialize a stack to do the undo operation. Then once this is done, add a task or a subtask. Okay, whenever you add a task, the parent task ID is empty, this field, okay, make this field as an optional field. If this is empty, it means that it is a new task. Okay, if this has some task ID which is already present in the system, then it is a sub-level task. If it is already has a task ID which is not present in the system, then also it is treated as a subtask, but it has to be created one layer below. And when you give the, there will be a status for every task. Okay, you are maintaining a structure. So every task will have a node ID plus it is the status, whether it is completed or whatever it is. So this complete task will change the status, whether it is completed or not. Okay, and undo, what it will do, it will change the status of the task from completed to in progress or not done yet. And redo will change the status again. So it is only changing of status basically in undo and redo. And display will display all the tasks. Okay, so you can do a simple command line loop. So enter the number of operations, add task. So it will add all this task. Complete task means the task ID will change to completed. Display task means it will display like this pending. What are the tasks which are pending? Okay, so you have to do a stack for undo and a linked list for managing task and subtask. You have to read both data from both while displaying the output. That's all. You have to initialize two things. Okay. So if you look at the implementation, it is simple addition, deletion, reading only, and change of data, update. Okay. So try to do this. If you have any questions, you reach out to me. After you complete, you can do the asymptotic analysis. And this is the split up of marks.
Ma'am, in deliverable source code means we need to copy that code and need to paste in WordPad.
Yes.
Okay.
Okay, ma'am.
Ma'am.
Yeah.
What need to be included, ma'am?
Sorry?
Ma'am, for third one in deliverables.
Just how do you are executing GCC or where you are executing those things? You will be doing if you're doing in our lab only, right? So then
Yeah,
GCC file is, VS Code file is will be there, GCC will be there. So just some instructions. Sometimes people don't use the lab, but I would recommend or make it mandatory that all of you use the lab provided. It's easier. You can save it there also. So just compile GCC and how do you read the instruction? Sample output you can mention there.
Okay, ma'am.
Screenshots also. So all this you can add to one Word file and submit.
Okay, ma'am. Ma'am, also in between we need to use the structures, right? C structures
Yes,
to define the.
yeah, this node you have to structure only, right?
Yes, yes.
So for a list, what is one task means what it will contain. This ID it will contain, plus it will have a status. So that structure you have to define. And it will also have a pointer to the subtask, next task, like that. You have to use it. Okay.
Until now I gathered few structures. Let me verify. One is for task and one is for task snapshots and one is for operations to do task ID, previous status, new status ID to include that. And another one is one simple stack, history of undo and redo for that one structure. And another one is task manager.
Why do you want task? You had operation of task itself, right? So why do you want task manager again? Undo, redo, stack is needed. One list is, you define the node structure in the list and all the operations also can be in the same structure, no? Update.
Yes, we can.
You don't need a separate task for it.
Okay. Ma'am, do we require any enums also?
Enum, I don't think so. Are there any static, say you want to put status completed in progress like that, you can use enum.
Okay. Okay. Because in C we don't have any OOPS concept, right? That way interface and all those things.
So it's okay.
Okay.
So with structures.
Hmm.
I will ask probably the lab instructor to give you more insight. I will ask the faculty to give inputs. Hmm?
Okay, ma'am.
Sure. Okay. Thank you. Just give me some time. I will just open the AVL thing.
Okay, ma'am. Sure.
I'll just be back in a minute. Just give me some. Okay. So let's get started. So today, let me see if recording is enabled. No? Yeah. Okay. So today, what is AVL? First, we will see that. So we had been learning binary search tree from the previous class. So binary search tree it is a balanced, it has to be a balanced binary search tree. So when we discussed that in the previous section, that when a node uh, is skewed towards one side, right? We say that the left side node should be less than the root node and right side node should be greater than in a binary search tree. That is the order. But what happens when you insert like that? Sometimes the node or the tree will get skewed towards one direction. Instead of it being balanced, it gets skewed towards one direction. So what happens when you have it in a skewed option? I already discussed this multiple times when we discuss trees. So when you have a height of the tree as order of n, all the algorithmic operations you perform on that particular tree will also have the time complexity in terms of order of n in the worst case. Whereas when you have a balanced tree like this, the operations also will be in a much more balanced way. right? So order of log n will be the best case. So when you have a skewed tree like this, you have it in a way that it is the operations also, the time complexity will increase. It will be order of n. But you will have it in order of log n. So it is always better if our tree is a balanced tree. All insertion, find elements, etc. will be order of h only. So AVL tree, AVL stands for the inventors, Adelson, Wilksey, and Landis. It is a balancing binary search tree, self-balancing. So what we mean by balance is there is very less difference. It's not skewed towards the right side or left side, but it is balanced on both the sides, right? In an AVL tree, the height of the two child subtrees of any node should differ at most by 1. If at any time they differ by more than 1, rebalancing will be done or the tree nodes will be rearranged in such a way we restore this property. So you have to understand it is a self-balancing binary tree. So binary search tree has to be balanced. If it is not balanced, AVL tree will self-balance it automatically. How do you self-balance it? That is a concept called rotations based on which we will self-balance. First of all, let's understand what is a balance, etc. All AVL trees are balanced only. Okay. An AVL tree is also a binary search tree. So when I say binary search tree, what is the rule? Root element should always be greater than the left side and right side element should be always greater than the root element, right? So that rule is already followed. In addition to that, the binary search tree rule, in addition to that, there is one more rule that the heights of the children cannot differ more, at most 1 only. It cannot be more than 1. So when I say it can be more than 1, it can be, it cannot be more than 1. I'm saying it can be -1, 0 or 1. It cannot be, when I say -1, the other side is greater. That's what it is meaning. So it can be mod, or we can say if you take, it should be plus or minus 0, 1. 0 or plus or minus 1. Okay, so that is how, so how do we find out the balance factor, or what is exactly when I say balance? If you look at this tree here, right? What is the height of a tree? How do you calculate a height of a tree? The number of nodes from the root to the leaf node, right? So if you take this particular subtree, this 4, right? How many nodes are there from the root to the leaf? Only 1. And 62 also only 1. So height of 48 or this subtree is 1. What is the height of this subtree? How many nodes are there from the root to the leaf node? 2. So the height of this subtree is 2. The height of this subtree is 1 because the height of the node, that is the number of nodes from the root to the leaf, is only 1. So this is the height of this subtree. Now, what is the height of 78 subtree? How do we calculate? So this is the root node. From this, the largest path, right? So if you take this path, it is 3. This part, it is 3. But this path, if you take, it is only 2. But whenever the height of the tree is calculated, the longest subpath is only taken into consideration. So the height of 78 is 3. Okay. And similarly, the height of this subtree is 2. But when you calculate the height of 44, that is the entire tree with root node as 44, always you have to take the largest one. So its height is 4. So the height we have, right? So when you have such heights, how do you find the balance factor, right? So if you look at this 4 as this, and the child of 4, there are 2 childs for 44. One child has a height of 2, other child has a height of 3. So how much difference they have as a balance factor? It is only 1, right? -1. So it is a balanced tree. If it is more, say this height is 1 and this is 3, right? Say you have a tree like 44 and this side you have only 17 and this side say you have 78, 50 and 48. So the height of this is 3 and the height of this is 1. So 3 minus 2 or 1 minus 3. So the height balance factor is 2. So which means this is not a balanced tree, but this is a balanced tree because the difference in height for the children cannot be more than 1. So that is what we call it as an AVL balancing. So what is a balance factor? It is a difference in the height of the left and the right subtree. And the balance factor should be 0, 1 or -1 for every node in the tree, not only for the root node. For every node in the tree, the balance factor has to be maintained. So the balance factor of a node is defined to be the height difference, height of right subtree minus height of left subtree. That is the balance factor. And a binary tree, the balance factor will be -1, 0 or 1. When it is less than 0, it is left heavy. When balance factor is greater than 0, it is right heavy. When it is 0, it is balanced. Okay. One minute, I will just show you some examples. Okay, so here we have a sample AVL tree. You're able to see my visualization window, right? I'm going to use the same visualization tool. Is it visible?
Yes, ma'am. It
Okay.
is visible.
Okay. So now you have a tree like this. Okay. Now tell me what is the height of this? Height of 32 is 0. Sorry, the height of 32 is 1. Height of 29 is 2. Height of 20 is 2. Sorry, 3. 65, what will be their height? It will be 3, right? So now this is a balanced tree or unbalanced tree? How do you decide whether it is a balanced tree or unbalanced tree? Okay, let me do this example in the slide. So let me copy this. So I'm going to insert 17. Okay. So now if you look, they are checking the balance factor. Whether the difference, what is the balance factor for each of the nodes? So let's do this balance factor checking here in the slide. So I've copied the node. Okay. Let me take some other color. Okay. Now what is the height of this node? 32. It is 1. Height of 29 is 2. Right? What is the height? The number of nodes from the root node to the leaf node. So this, for this subtree, this is the root node and 2 nodes are there. So height of 20 is 3, height of 11 is 1. Okay. Why height of 20 is 3? One side it has 2, other side it has 3. So the largest will always be taken. So that is why it is 3. Now, if you look 72, it is 1. 99 also height is 1. 50 also height is 1. 91, the height is 2. And this will be 3. And for this, it is 4. Okay. So this is the height. So how do you calculate balance factor of a node? Height of right tree minus height of left tree. Okay. So for root node, what is the balance factor? So for root node, what is the height of right subtree? It is 3. The left subtree is also 3. So the balance factor is 0. Okay. For this 20, what is the right subtree height? 2. Left subtree height is 1. So the balance factor is 1. For this node, right subtree is 0, left subtree is also 0. So the height is, balance factor is also 0. For 29, for this, it is also 0. For 29, the height of right subtree is 1. The height of left subtree is 0. So the balance factor is 1. For 50, it is 0 balance factor. For 72, it is also 0. For 99, the balance factor is 0. For 91, 1 minus 1, balance factor is 0. For 65, it is 2 minus 1. So the balance factor is 1. Okay. So this is the balance factor. Now all the balance factors are within the range. 0, all the balance factors you can see it is within 0, 1 or minus 1 only, right? So it is a balanced tree. Now, what are we going to do? Every time you do some change to the tree or you insert something to the tree, right? That is when you will see also check whether it is unbalancing the tree. If it is unbalancing the tree, we have to correct it. Okay. So let's say I'm insert 17. Okay. How do I insert 17 in a binary search tree? How do I do insertion? My PPT is visible, no, Sri Vignesh?
Yes, ma'am, it is
Oh,
visible.
okay. So how do I insert? I check with the root node. If it is lesser, I go to the left side. If it is greater, I go to the right side. Right. So I check here, insert. It is lesser. 17 is lesser. So I go here. Again, I check here with 20. It is lesser. So I go to the 11 left side. Now it is greater. So I have to go and insert here. So I will insert 17 here. Now by inserting 17, there is balance factors will change. So I have to identify what is the change in the balance factor. Now what happened to the balance factor of 11? The right subchild BF of 11, balance factor of 11 becomes right subtree is 1 minus 0. So this 0 becomes 1. Why it becomes 1? Because the height of the tree has changed. Okay. So this height of the tree of 17 is 0. The height of, this is 1. The height of 11 has become 2 now. Okay. So the balance factor becomes 1. Okay. Now what is the balance factor of 20 now? Balance factor of 20. What is the height of the right subtree? It is 2. What is the height of the left subtree? It is also 2. Okay. So the balance factor of 20 also becomes 0. So this becomes 0. Okay. Now, is there any change in the balance factor of 41? No, the height remains the same, right? It is 3 here. It's also 3 here. So the height remains the same. So there is no change in the balance factor of 41. Okay. Now let's say I add 36. Okay. What will happen? Okay. That's what I'm going to show you in the visualization. So 17, I had it. It's the tree is balanced when I added 17, right? So now I'm going to add a number 36. So it will check for 41, 20, 29, 32 and 36. It will add. So now it is checking the balance factor. So what happened? Sorry, 1 minute. Okay. So in this tree, what is the problem now? When you add 36, the balancing is disturbed. Okay. So it has to be restored. How do we restore it? We restore it based on rotations. Okay. So I will tell you how, first of all, I will explain why balancing has so next I'm going to insert 36. Okay. So where 36 will be inserted, it comes here, it goes to 20, 29, then 32, and here we will insert 36. So when we insert 36 here, what will happen? First, height of the tree, what will happen? The height of this tree will be 0. The height of this tree will become 2. The height of this tree will become 3. The height of this tree will become 4. Right? So, and the height of this tree will become 5. Now you have to check the balance factor. So when you check the balance factor, what is the balance factor for this node? It is 1 minus 0. So the balance factor becomes 1. What is the balance factor of this node? 29. You can see the right side height is 2. The left side height is 0. So it is 2. Balance factor of 29 is 2 minus 0, which is 2. So the balance factor becomes 2. So when balance factor can be only 0, 1 or minus 1. Right? So it is 2 means the tree is not balanced. So now this balance factor will also affect all the other balance factors, but this is the first subtree which is affected. So if you correct this, all the others also might be cleared. But if you look at the balance factor of this, what happened? This height has become 3. This height has become 2, right? So 3 minus 2, it is still 1. The balance factor again has become 1, right? This balance factor is become 1. Okay, so here there are no problem, but here this tree has become. So or any node which has a balance factor with not within this range, it is a unbalanced tree. Okay, so insertion, deletion, or any change we are making to the tree, mostly insertion and deletion, will unbalance the tree. So how? So whenever you have a lookup insertion, you have to rebalance the tree. You have to do tree rotation to make it balanced. How do we do rotation is what I will explain in detail. But what is the time complexity? Since the tree will always be balanced, right? All the time complexity, lookup, whether it is read or insertion or deletion or search, will always be log n time because the tree is always balanced on the left and the right side. So it will not be skewed. So it is always have a log n time complexity in a AVL tree. Okay. So read only operations, there is no change. How do you do binary search read? Right? Traversals, in order traversal, post order traversal, pre-order traversal. The same order traversals is what you will do in the binary tree also, binary search tree also. So read-only operations, there is no change, but modifications, insertion, deletions, you have to recalculate it. It is not only insertion, but you have to repeat an additional step after you do insertion or deletion. You have to check the balance factor of every node. And once the balance factor is done, you have to restore that node. Okay. So this is the idea. So searching is simple as you do in the same balanced or binary search. How do you do? The same is what you do. Traversal also is same. There is no change as a binary search tree, but the change happens only in insertion and deletion. Okay. So let's take a quick break here for 10 minutes. Come back where we will learn how to do the different rotations of a AVL tree. Okay, let's come back after a 10-minute break.
Okay, ma'am.
Okay, so let's continue. So we are going to see how to do rotation. So rotations will happen only when there is an unbalancing triggered by an insertion or a deletion. So when inserting a node, you initially follow the same process like you do for a binary search tree. If the root node is empty, you insert at the root node. Otherwise, you compare the value of the node and you check whether you have to go for the left side or the right side. So if it is lesser, you go for the left side, and if it is greater, you go for the right side. The traversal again is you have to go through the entire guided by the comparison. That is, you have to every time check whether you want to go for the left side or the right side, and then you insert the node. Now, after you perform the normal binary search tree insertion, you check the balance factor of all the nodes. That is, you have to check whether a tree becomes unbalanced. So how do you check whether you don't have to go and calculate balance factor for all the nodes? You have to check for the balance factor only for the ancestors of the newly inserted node. So if you are inserting on the left side, you have to check for the parent, grandparent, and the root node, etc. So only the ancestors. When I say ancestors, it means all the nodes which are in previous levels till the root. So all the nodes you have to check the uh, balance factor. Only nodes in that particular subtree will be unbalanced or changed. So you have to check for only those ancestors only. Okay. So for each node in the ancestor, you have to check whether the balance factor is changed or it is balanced or not. If there is a unbalance, then you have to change it. So if you insert a single node, there will be change in the height of the subtree. And this height of the subtree should not cause any balance factor with +2 or -2. So you have to check for the balance factor. If it is in the same -1 to 1 range, then you have to just update the balance factor and you don't have to perform any rotation. However, if there is any balance factor which changes to -2 or +2, then the subtree rooted at that node becomes unbalanced and you have to perform a rotation for that particular subtree. Okay, so in this example, you can see everywhere the node is balanced, right? You have to just update the subtree and add it. Okay. So how similarly rotation, I will come to it later. Similarly, deletion also will cause a change in the balance factor. So the same concept of binary search tree deletion is what you follow there also. So the effective deletion is replacement of the node will be from the ancestor, that is the in order successor or predecessor is what you will replace in a binary search tree deletion. So when you do that, you have to again check whether any of the ancestors have changed or any of the ancestors are having a balance factor greater than 1 or 0 or -1. Then what you do, you actually consider that that the tree becomes unbalanced. So this step you do, that is first normal insertion, normal deletion like you do for a binary search tree. The second step you do retracing. So you check the balance factor for all the ancestor. So based on the result of the second step, if there is any unbalance, you go to the rotation, which is the third step. If there is no unbalance, you don't have to do any rotation. You can stop with this step itself. So the balance factor should remain -1, 0 or 1. By any insertion or a single insertion or deletion, it can become -2 or +2. So if there is an unbalance, you have to go for the third step, which is rotation. So the rotation is nothing but rebalancing. So during any change we make, that is insertion or deletion, a height difference of 2 may arise when you insert or delete single nodes. So that height difference is that we have to correct, which is called rebalancing. So this is called as rotation because they move the keys, because we rearrange it in such a way it becomes balanced, but we have to ensure that the property of the binary search tree, that is the left side should be correct, right side should left side should be less, right side should be greater, and when you do an in order traversal you get a sorted list. So these are the properties of the binary search tree. So we move the keys, they are called as rotation because they move the keys vertically from one, that is we don't swap the left child and the right child like that. We only move them vertically within the same path so that the sequence is completely preserved. The properties of balancing is preserved. Okay. Now, how do we do balance? How do we make it balanced? By performing rotation. So there are 4 types of scenarios we will encounter, and there are 4 types of rotations for it. Okay. So first I will tell you the scenarios. So first is right, right. That is, this is a balanced tree, correct? Okay, if this is like this, right? It is an unbalanced tree. Okay, and if this is like this, again it is an unbalanced tree. If it is like this, is also an unbalanced tree. If it is like this, it's also an unbalanced tree. So we will have 4 scenarios, 1, 2, 3, 4. Okay. So when Z, so we can call them as Z, X, Y. Okay. So Z is a right child of its parent X, right? And the balance of Z is greater than or equal to 0. Okay. Then we have, so let me show with the rotations. So this is one option. So you have it this way. So you have to make it balanced. So this is LL rotation. Then we have this is RR rotation. That is you have to rotate right side because it is unbalanced. So then we have one LR rotation and then we have one RL rotation. Okay. So I will tell you those concepts. So there are 4 options, right, right, left, left, right, left, and left, right. In these, when right, right or left, left, both are skewed towards one side. That is the first option and second option, right? This will require only one rotation. So we call this as single rotation. But this, when you have this kind of a setup, you have to do a double rotation so that you get a balanced tree. So I will explain each of this in detail. So when this, so if you look at this particular example, what is the height of this? It is Z1. The height of this is 1, height of 3, right? So what is the balance factor for this node? It is 2 minus 1, 0, right? So it is 2. So the balance factor of this node is 2, which means it is unbalanced. So we have to make it balanced. So when you have this kind of an approach, right? You rotate anti-clockwise. So what is anti-clockwise? You rotate like this, right? That is what you rotate anti-clockwise. So when you have a left-left rotation, right? You rotate anti-clockwise. So you just rotate this tree like this. So consider you like a pulley. Okay. So you have, so usually you have to consider it like a pulley. Okay. Say you have a thread. Okay. This is like a thread. So 1 node is there, 2 node is there, and 3 node is there. You just pull this thread anti-clockwise. So this becomes, so this will move here. So 2 becomes on the top, 1 becomes here, and 3 becomes here. So consider like the pulley and a thread. So it will be easy for you to imagine. So now this tree, when you do this rotation, one rotation, you're doing only one rotation, one pull, and you are making the tree balanced. So this left rotation is like this particular node becomes the center node, and you have one left child and one right child, and you can see the properties of the binary search tree is also managed, is also balanced. The tree is restored its balance. So this is a simple single rotation technique when the tree is queued, and this is called as LL rotation. In an RR rotation, you rotate clockwise. The same concept here also, since it is R and R, you have to rotate right side only, in clockwise direction. So again, you will have a similar tree like this. In this rotation also, you do it single wise. You imagine like a pulley thread. So here you are pulling this way. So it is like 3, 2, and 1 is there. So you're just pulling this thread here. So you get this. So it is also a single rotation. Now, when you just skew to one side, it is a single rotation is sufficient. But this requires a double rotation. If you, this is also unbalanced only because the height of this is 1, the height of this is 2, and the height of 3 is 3. Now, if you look at the balance factor for this node is 1, but the balance factor of 3 is 2. Because here it is 2, here this side it is 0. So the balance factor is unbalanced. So in order to achieve the balancing, here first we have to do a rotation of this L. So LR rotation means LL plus RR rotation. Okay. So LL plus RR rotation means what you have to do, you have to first consider this thread where you will pull it anti-clockwise. So this first you do a LL rotation. So this becomes 3, 2, 1. Okay. And then you do a RR clockwise rotation. So it becomes 2 and 1 and 3. Okay. So LL rotation plus RR rotation is what LR rotation is. So it is a double rotation. You cannot achieve when you have a node like this, you cannot achieve the balancing in one step. So it is a two-step balancing. So first step is a LL rotation where you get this approach. Then the second step is again an RR rotation where you get a balancing. Okay. So LR rotation is called as double rotation because it is done in 2 steps to take the tree to a balanced position. Similarly, RL rotation also, it is a 2-step process. So first you have, so this becomes 1, 2, 3. So you do a rotation of this. First you do a RR rotation and this becomes like this. And then again you do a LL rotation anti-clockwise. So it becomes this. So again here also you do a 2-step approach. So it is called as double rotation. Okay. So after the rebalancing is performed based on the requirements, your tree will become balanced. Okay. So right. So this is a balancing factor here. So you can see the balancing factor is 2 plus 2 here, right? So here you just do a single rotation. Similarly, in a left rotation, X is brought to balance with a simple single rotate right? It is like a mirror image of that. If you look you will see in single step, you are able to achieve it. But in case of a double rotation, right, left and left, right, you cannot do this in a single rotation. So first you have to bring this Y and all of them in the same line. And then again, you have to do the balanced rotation. So this is the summary. So there are 4 ways in which you can do rotation. In a single rotation, you just do, if it is LL, you have to just do an anti-clockwise rotation. If it is RR, you have to just do a clockwise rotation. Okay, so this is this way, this is this way. In a double rotation, you have to do 2 rotations. So first LL rotation and then RR rotation. Here, first RR rotation and then LL rotation. So then only you will get the tree, a balanced tree in an ABL rotation. Any questions till now? I will show you visualization example, but any questions before I start? No?
Ma'am, will you show the demo code? How do we can perform that?
Yes, yes.
Okay. Ma'am.
Okay. So insertion is a binary search tree. Let's look at. So before insertion, it is like this. And now we are inserting 154. So what happens now? Say this is our X, Y, and Z. The balance factor has changed. This is a balanced tree, but here this becomes unbalanced after insertion. So now we have to do a restructuring. So always in restructuring, 3 nodes are considered. So that's why it's known as tri-node restructuring. Okay. So in case of a single rotation, okay. So here you see, you calculate the balance factor in this case. So for example, say, what is the height of this tree? It is 1, this is 2, this is 1. Right? This is 1, this is 3, right? This is 1, this is 2, 4. Okay. This is 5. If you calculate here, this is 1, this is 1, this is 1, this is 1, this is 2, this is 3, this is 2, and this is 4. So if you look at this tree, the balance factor is all same. But if you look at this tree, where are the balance factors affected? So this subtree does not have any problem. This subtree also does not have any problem. Its balance factor is right only. But here is the problem. So this node 78, the balance factor is 2. And similarly for 44, the balance factor is 2. So this is the problem. So we have to take this subtree, the problem has occurred. Okay. So when you have the tri nodes, should consider this. Okay. So this is the rotation we have to perform. Okay. You inserted here, so you should not consider this rotation. Why you should not consider this part of the tree? So 50, 62, 54 we need not consider because 50 balance factor is correct. 62 balance factor is also correct, 54. So when you insert a node, the tri nodes which have to be considered, the 3 nodes which has to be considered for is which is the lowest level where the balance factor is incorrect or the balance factor is unbalanced. So these three nodes is what you have to take into consideration. Okay. Now tell me 78, 52, 62, what kind of a restructuring it has to go to? What? Okay. So this is a left right rotation, right? So first we have to do a anti-clockwise rotation. So it becomes 78, 62 and 50, right? And then we have to do a clockwise RR rotation. So it is LL, LR rotation, LL plus RR rotation. So 62, 78, 50 will become the balancing, right? So we will make this 62 will come here, 78, 50. Okay. We have to do this. Now you have to attach these nodes. So where will you attach? So when you do this restructuring, what will happen to these nodes? Right? So you have to attach them in the right way. Okay, so let me show you how this is done in through the visualization. Stop sharing this and share the visualization. Okay, I will create a new tree. Okay, so we have a tree which is created. Now let's insert some unbalanced nodes, 36. Okay. So 36 will be inserted here. So as soon as 36 is inserted, which node becomes unbalanced? 29 is the node which becomes unbalanced. Okay. So these are the three nodes which has to be considered for the, I will replay it. So this is the balancing. So these are the three nodes which has to be considered, 29, 32 and 36, which has to be considered for the rebalancing. Now what kind of rotation we have to perform on this rebalancing? It is skewed towards the right side. So it is a simple anti-clockwise rotation we have to do. So we have, it's a single rotation. So it becomes 32 becomes the root node and 29. So a simple rotation is performed. Now, when you do the simple rotation, you can see the balance factor, the tree becomes balanced. Okay. So now let's insert 79. Okay, so when you insert 79, the 72 subtree is balanced. This 91 subtree is also balanced because this side 2 you have 1 only. So the difference is only 1. But 65 is the one which becomes unbalanced. Okay, so this is the tree which is become imbalanced. So I will show you. Okay, so this is the balance problem, right? So 65, 91, 65 has a balancing of -2 because this side you have 3 and the other side you have only 1. So this is the balancing factor is -2. So what are the nodes which should be considered for balancing 65, 91 and 72? So this is a double rotation you have to perform. Okay, so this double rotation has to be performed. So I will replay it so you can see it. So now 65, 91, 72 has to be rotated. So 65, 91, 72 is a double rotation. So first 72 and 91, they have to do a clockwise rotation. Okay, so you can see 65. Sorry. So this way 65, 72, 91 has come in a straight line. So one rotation is over. Now the second rotation has to happen. So now 72 becomes the node and it is attached to the root. Now you can see that what happened to the other nodes, the left side node remained as such, the right side node remained as went to this. So you'll observe. Okay. So you can see what happened to this node when you 65, 91, 72 is what you are rotating. So when 72, once first single rotation happened, you can see that 79 has been moved to the left child, right? As such, you move that nodes. Okay, so that is something which you have to understand in the tri-node restructuring. So this example, if you have to very carefully remember that how to replace the entire child. So this triangle boxes which you are seeing, right? These are the triangle boxes as such has to be replaced. Okay. So in terms of this, right? This is the node. These are the three nodes. Now this becomes there. Now what happened to T1? What happened to T1? It becomes the right child of this node. So this is something you didn't observe in the previous. So we were only concentrating on these three nodes, right? So we didn't know what T0, T1. T0, T1 are nothing but the subtrees. Okay, when it is happening in the leaf nodes, this T0, T1, T2, everything will be empty. But when it is happening in the middle or in the levels upper, this has to be attached appropriately. So you can see in this single rotation, this is the first LL rotation. This C nodes T2, T3 remain the same. But for B, whatever child is there in this side, it goes to the right child of A. Okay. Similarly, in this right rotation, you can see this T2 goes to the left child of A. Sorry, right child of A. Okay. So the whatever node is shifted, you have to understand how this is also copied. Right. So similarly, in a double rotation, what will happen? So in a double rotation, you do two rotations. So first this becomes like this, right? A, B, C, right? So what happens during that when it becomes A, B, C, this T1 will remain here. Okay, but this T2 will be added to this C. So it becomes here. So that's why, and in the next step, this T1 also will go to A. So you can see this left child of B goes to A, the right child of B goes to C. So in the final, you will see B, the T1 is here, and T1 is here and T2 is here. Okay, and similarly in this also you can see in the first rotation it will be C, B and A. So what will happen to this T2? T1 will remain here only. T2 will go here and T3 will remain here and C will have this T0. In the second rotation, what will happen when B becomes the parent? This T1 will be attached to the left side of C, T. So that is what exactly we have to do here also. So in this case also, we are going to look at this nodes 78, 52 and 62. So what will happen? First 78, sorry. So we'll take out these nodes separately, 78, 50, 62, right? So on 50, we have 48. And in 62 left side, we have 54. And here also we have 88. Okay, but these are the three nodes we will consider. So first this has to be changed. So how this will change now? So 7. So this will change 78. This will go up 62. So first anti-clockwise rotation. So this is how it will go. Right now, what will happen to this 54? Right? What will happen to this 54? This rotation. This is what. So what did happen to this T2? It was attached with A, right? So A is 50, right? So it will be attached. So this 54 will be attached here. And the 48 of 50 will remain as such. The 88 will remain as such. So first in double rotation, one part is completed. Now again, what will happen for these three nodes? You have to again do the second rotation. So the second rotation, what will happen? 62 will become the parent node, 50 will be here, and 78 will be here. So this 50 will retain 48 and 54. And this 78 will have the 88. So this is the final subtree which will be here instead of this subtree. Okay. So you can see this answer which I just worked out for you. So this was the 78, 50, 62 is here. Okay, so this becomes 62, 50. So this 54 went into the left side and it was rotated. So this is the final output. So you can see that the tree is now become a balanced tree. Okay. Let's do one visualization example so it will make it very clear for you. Because only when you do multiple examples, you will get this concept. It's otherwise in first time, you will not get it. So please practice more. So let me create a sample random tree. Okay, so let's do an insert of 16. So 8, so it will come here. So the tree is balanced. So there is no unbalancing because of this insertion. So it stops at this place. So now we will do another insertion of 34. Okay. So this is balanced, but 8 becomes unbalanced. So now 8 is unbalanced, right? So 8, 37, 16 are the nodes you have to balance. So what kind of rotation it is? You have to first do a anti-clockwise rotation, LL rotation, and then you have to do a RR rotation. So what will happen? First 16 will go up, 37 will be attached. This 34 will be attached to the left side of 37. So this is what you get. Then again you do a second rotation where 16 will go up, 8 will come to the left side of it. Okay. So now the tree becomes balanced. Okay. Let's add some number like 87. So here it's a single rotation. So you just do the rotation and you can see the tree becomes balanced. Is it clear, Vignesh? Any doubts in the rotation?
Yes, ma'am. Until now, I have no doubts cleared.
Okay, fine.
Ma'am, give me one more example, ma'am. I will try.
Okay, you want to try, definitely. So let's insert 2 in this tree.
Okay. Ma'am, after 1, it will be insert, right?
Yes. So first you have to check with 47, it is lesser. So you go
Yes.
to 16, it is lesser.
Yes,
You
sir.
go to
Yes,
8,
but
it is
wait.
lesser. So it will come where? Right side of 1.
Yes.
So when it comes right side of 1, which are the 3 nodes which become unbalanced?
Mm.
Okay. So now what is when this is become this? 1 is balanced,
Yes.
right?
Yes.
But 8 is unbalanced. So which are the nodes which has to be altered? 8, 1 and 2.
Yes.
So what rotation you will do?
Ma'am, we need to do left,
Yeah, I will
left,
share the
left, I
slide
think,
for you. It is single or double rotation.
and double rotation.
So it is double rotation. So which rotation? LL or RR? Sorry, LR or RR? This is
LL and RR.
LL and RR rotation you have to do,
Yes.
right?
Yes.
So now when you do, sorry, I will reshare. So first in single rotation, what will happen? 8, 2 and 1 will come on the same line.
Same line. Yes.
Okay. Now again you have to do a rotation. So 2 will become the root center node. 8 and 1 will be the children of that.
Yes.
Okay. So now let's do another insert. Say we can insert some eighties five. Okay. Where will it come? Okay. Now tell me which are the 3 nodes which are balanced becomes unbalanced because of this. Is there any unbalancing? or the tree is balanced?
81, 87, 85. Think so.
Balancing. All the balance factors are correct only. No. Why do
Yes.
you think it's the balance? So there is no rotation required
Okay.
because all the tree has been balanced. Everywhere balance factor is 0, -1 or 1 only. So there is no changes required. Now let's say I do insert '86. Okay. Now what happens? This becomes unbalanced. Okay. So when this becomes unbalanced, what will happen? 87, 85, 86 has to be balanced. So first rotation will make it first 87, 86, 85 rotation will happen. And then this rotation will happen. Now the tree is balanced.
Balanced. Yes.
So if you see this orange color, follow this orange color, you will clearly see that the balance factor is not checked for all the nodes. Okay. The balance factor is checked only for the, if you see, it is checked only for the ancestors. So you can see 86 is checked, 81 is checked, 88 is checked, and 47 is checked. So you have to check the balance factor because only those path in the ancestor, that is where the balance factor will change. So you have to check till the root node. You shouldn't stop. Sometimes we will check, okay, this is balanced, this tree is balanced, so it is fine. And we will leave the ancestors. But there are situations in which the balancing will happen at that particular point of, even in the root node because of it. Okay, now let's do deletion. So insertion, deletion is nothing, same only. But when you delete also, the balance factor will change, right? So you have to first perform a normal deletion. And if there is an imbalance, you have to again do the same rotations. That is what in deletion we will do. So removal, you do as usual in a binary search tree. So you remove that node. So say 32 you want to remove, you just remove that node. But when you remove after deleting 32, what happened? The tree has become unbalanced. Now, what are the nodes which has become unbalanced here? Tell me what is the balance factor here in this example. So balance factor for this is okay. Right, first let's light the height. So this is 1 height, this is 1, 1, 1. So this is 2, this is 2, this is 3, this is 4. Right? So balance factor is correct everywhere except this node. Right? So 44 is where unbalancing happens. So the three structuring nodes should consider this only. Okay. So 44, 62, and 78, 50. Okay, so how do you make this balanced? So we have to restructure that. Okay, now 44, 62, and 78 we have to take into consideration. Okay, so this is, since it is a only single rotation, 62 becomes the center node, 44 goes to the left, and 78 becomes the right. So the children of 78 are directly as such mapped, but the children of 62, the right children of left children of 62, they are put into 44's right children. So it becomes here, copied here, and it becomes copied here. Okay. So let's do some deletion in the visualization. Say let's remove 2, 8. First, let's remove 2. Okay. So when we remove 2, there is nothing difference. It will not change. So now let me remove 8 and 1. Okay. Now let's remove 1 also. Okay, now the tree becomes unbalanced. So you make it balanced. Okay. Now if you look at this previous step, when 16, if it was this like this, right? So what happened? 37 went. So the left child of 37, which is 34, was marked as the right child of 16. So as such, you have to copy. So this is where many people do the mistake. When you do a rotation, you have to understand what kind of rotation it is, and you have to copy the children of the subtrees as such there. Okay. So now the tree is balanced. So now let's say we will do some remove of, say, 16 and 34. Okay. So you see what, when we remove 16, what happened? So 34. So in this step, what happened? 47 became unbalanced because here it is only 3 and here it is 5 nodes are there. So this becomes unbalanced. So where is the unbalancing? Not in 37. So it is 47, 88 and 81. Right? So that is the long path where the heavy weight is there. So you have to, so 47, 81, 88, 81. So these are the 3 nodes where the unbalancing has to be balanced. So first you 47, 88, 81, that is where you have to do the rotation. So every time the rotation, how it is, the 3 nodes you choose, you have to choose it wherever it is the longest, heaviest. you have to balance it so that the other side is compensated. So 81 becomes the center node. So first rotation happens, then again a double rotation happens. So you can see the left child of 81 becomes the right child of 47, and 81 becomes the root node, which makes the tree balanced. Now again I delete the 34, but this doesn't change any balancing. So the tree is balanced. So in deletion of the AVL tree, so you first start with normal deletion as you do. And while traveling up the tree, you will see where the first unbalanced node is there. And you will check for the one with the largest height and you will do the balancing. If one of the children of Y is taller, then you choose that X as the path where you will do the restructuring. If both the children have the same height, you choose the path where you have the same side of Y. Okay. So in this case, if you see that this 62, both the children had same path. So same side as Y. So Y is right side. So you have chosen the same side of Y. So this third condition is what you have selected. So these are the three nodes, 44, 62, and 78. These are the three nodes which you have restructured. Okay. So 44 is becoming unbalanced means you have to choose 62 and whether you choose 50 or 78 depends on how the restructuring is there. So if one of the children of Y is taller, okay, say this is already having one more child here, this is the taller, so then you will choose this. Okay, if one of the children is taller, you choose that as Y, but if since both have you choose that as X. Since both the children of Y are of the same height, you choose the same side as that of Y. Okay, so this is the how do you choose the three nodes for restructuring? So in this delete 4 is we will see example. So delete 4 causes an imbalance at 3. So now what are the three nodes you have to choose? So this is your node. And this is the balance. This you have to start from the node where the balancing. So let Z be the first unbalanced node encountered, right? So first node which is encountered in unbalancing, right? When you remove this balance is right, this balance is wrong. So the first node which is encountered is 3, right? So 3 becomes your Z. So this becomes your Z. Now, how do you choose Y? Y be the child of Z with the largest height. So we have only one child, so this is becomes Y. If you have some other child, then whichever is the largest height, that will be the Y. Then how do you choose X? Again, X, if there are two children, again, how will you decide which is the right one? You have to see whether they are of same height. If they are of same height, you choose whichever is the largest. If they are of different height, you choose the same side of Y itself. So here we have only one children, so this will be our X. So now it's just a RR rotation. So you have to just rotate and you will get this tree. Okay. Now, so what is the unbalance? So you have done this rotation, right? You perform rotation at 2. So you have got this, right? Now, is this balanced or unbalanced? So here the height is 4. This is, sorry, this is 5. This is 4. This is only 2. So again, it is imbalanced. So which are the nodes which are imbalanced now? Where is the balance factor incorrect? Here, right? So you have to choose 5, which is the first node where the balance is incorrect. It is 5, 8. So in 8, you have to choose the node with the longest 7 and 8, whichever is the height is the longest. So you choose these 3 nodes. So you perform a rotation. So 8 becomes the center, 5 becomes the left side, 11 becomes the right side. So 8's left children will become the children of left children of 5. So 7 and 6 you just copy to the left side. So whatever to the right side, whatever was to the left side, you copy as such. And 11's, whatever was to the child of 11, you retain it as such. Okay, so the tree becomes balanced. So a single restructure is order of 1 because you are using a linked structured binary tree. You just have to change the links. And always when you want to do a find, since the tree is always balanced, it is always order of log n only. So no restructuring at all is required. Insert is also always log n because the tree will always be balanced. You are maintaining the tree. Removal is also order of log n only. Okay. Now, why are we actually balancing? What are the advantages? Always we get a log n optimized result. So you have the tree sorted. You are able to perform insertion, deletion easily in a binary tree. It always takes, since binary search tree, the search is also log n. It is easily can be added to remove elements because you don't have to search through the entire tree. You search only half of the elements. If it's greater, you go to the left side. If it is, if it's lesser, you go to the left side. If it's greater, you go to the right side. So only half you are always changing. So always it's an optimized tree. Since it's always self-balancing, all the algorithms will run in logarithmic time. That is the advantage of this particular AVL. So I will stop here for today. Any questions?
No, ma'am.
Okay. So next class, we will continue a few more things in AVL and we will go to the next data structure, which is heap. Okay.
Okay, ma'am.
So in the lab, did you implement something? In the lab sessions, you had 2 lab sessions, right? What was the implementation you did?
Ma'am, once I rewatched the session only, ma'am. Did not try
Okay.
the implementation.
Okay. But what was it implemented? I'm asking. Where did you demonstration was shown to you, right, to implement?
Yes.
Okay. Fine. So the upcoming implementation, we will work on tree and other heap-based implementations. Okay. Okay, thank you.
Okay, ma'am. Thank you.